In 2010, I lost the 6.0 motor in my 2003 F350. That was my own fault. At the time, I was taking care of my mother who had dementia and could not do the repair on the motor itself, or install a salvaged motor. So I opted to purchase a Ford remanufactured motor at the dealership. This was a hard decision. I came very close to just letting the truck go as a rolling chassis. I'm skeptical of aftermarket rebuilds, but this motor was a Ford certified product, with a premium price and a warranty. What could go wrong? I feel compelled at this point to explain my credentials, as people I worked with find this situation incredible. I spent 30 years working for a major automotive supplier, to Ford and other automotive manufacturers. The majority of this time overseeing the research and development vehicle testing group. Some people could characterize it as product testing, finding faults before the customer does. I did that very well. If you drive a Super Duty, I was one of the thousands of people in the developmental process. I was never a manager who stayed behind the desk. I worked on the test vehicles, I drove them, and I wrote the detailed reports about the product test results. I've built and raced motorcycles. 66 Mustangs and Shelbys are a hobby. And I've held more ASE master certifications than anyone else at my old company of 40,000 employees. And I've worked in a machine shop. I've been around the block. I'm retired and don't sell repair services, so I have nothing to sell here. After some time, there was something not right with this motor. After an hour of driving, I could hear a noise at full speed. This noise drove me crazy. A service manager in a Ford FSE thought it might be an injector with a slight tick. Wait for the code. It didn't sound like an injector or a rod. Maybe some piston slap, as I've heard on some GM motors. On long highway drives, it would get worse, as everything was thermally soaked. And I would get out and try to record the noise, but it was hard to notice at idle or outside the cab. I ran hours of IDS tests trying to find a problem injector. It showed some inconsistent results, but nothing concrete. Cold relative compression tests showed a slight loss in cylinder 2 that resolved once the motor was warm. So nothing proved consequential. I even tried recording the noise on back roads while driving. Or I could pay the dealer to tear down the motor with a $3,500 gamble that something might be found under warranty. Ending a 200-mile run, this night was the last time the truck saw it long-distance driving. The truck was sitting for weeks at a time rather than being driven every day. A person in a forum had an alternator issue, so I did a video about the battery light. At first start, this characteristic showed up. April 4th jump. The death cry of a valve train issue. April 4 start. Or was it? Using the acoustic readings from iMovie, it showed a spike in volume that the human ear has a hard time distinguishing.
Checking 2 and 8 at top dead center.
An inspection of the valve train under the rocker arm cover didn't show any issues.
Number 5 exhaust.
So with the hope that a push rod had bent, I first rotated the crank a dozen times to pump out the lifters so I could take a base reading of valve lift. And number 8 exhaust showed a reduced lift. This could be a bent push rod, a destroyed roller lifter, a wiped cam lobe, or an internal fault within the lifter itself. So I installed the Bosch tool to depress the valves and remove the rocker arm so the push rod could be removed. And it was straight. The first step was to build engine plates for an engine stand. Then removing the motor. At 9 years and 75,000 miles of service, way past warranty. I disassembled motors in the reverse they are built, following the fastening increments and patterns. If we tighten to not stress or bend parts, we should do the same when removing them. Looking at the driver's side head gasket, we can see carbon has been deposited in the thin area that coolant wanders through. There are defined orifices in most head gaskets to control bleed air out of the top of the cylinder water jackets. But these areas also allow some coolant to pass through the gasket area, keeping it cool. When there is combustion leakage, we see the remaining carbon deposits. However, this side of the gasket, the head side, does not show the typical blowout. This image from the internet shows a typical blown head gasket, with the burning of the metal and sealant. This head has crowned. With a closer view of my motor, cylinder 2 shows minor carbon at 11 o'clock, the sealant intact. Cylinder 4, 6, and 8 show carbon, but all the sealant surfaces are intact as well. No blowout. Looking at the driver's side head surface, it mirrors the gasket. A close-up view of this gasket shows that the sealant is relatively intact. And some Scotch-Brite cleaning of the head surface shows a smooth surface. I had to make a composite from several images, so this appears distorted. The block surface shows more carbon, and it's distributed differently on this side of the gasket. As we look closer at cylinder 2, it becomes evident that rough machining marks are visible, and an increase in carbon deposits. Cylinder 4 also shows the issues, just more so. Cylinder 6 to the left and right. Cylinder 8, more pronounced. The deck surface was then cleaned using a chemical gasket remover and paper towels. And the machining milling marks are more visible, without as much carbon contamination. And to quantify the worst area with a profilometer. The better end, with some stoning work, gives hope this can be DIY corrected. The inspection of the gasket surface shows the Ford gasket sealer extruded into the machining marks, trying to meet its purpose, to fill any irregularities. In some areas, the volume of material extruded left a deficit at the boundary to seal. It tried to work. There just wasn't enough volume of material. The surface was starved. And with this starvation, you can have slight leakage, especially when starting a cold motor before the head expands from higher temperatures. The passenger side gasket showed the same trait towards the head surface. Carbon leakage, but no blowout at the fire ring in the center. The passenger side cylinder head displayed the same traits as the driver's head. Without any cleaning, we can see different machining marks than the driver's head. That will be discussed in a different video. But it still matched the presumed International Ford spec of 30 RA for surface finish. As with the driver's side, the gaskets look good, and the sealant looks intact. The block deck on this side is unusual from my experience. It has the appearance of being media blasted over the milling marks, but the milling marks are lightly seen. It begs the question, when this block was reworked, was this side skipped over after a cleaning media blast, or was it not resurfaced because the deck height was already at the lowest it could be? The gasket surface doesn't show the channels of sealant pathways, but does show migration. Once lightly cleaned, the heads did not show any immediate problems. They were machined on different types of equipment, leaving different characteristics of surface finish, one around 20 RA and the other around 30 RA. Both showed some bowing, but within tolerances. And valve recession was consistent and in specification. One cylinder head was at the minimum thickness allowed, but with only 75,000 miles of use, these should be fine. An inspection of all the lifters showed no visible issues. The surface of the rollers or wheels were good, and the bearing didn't exhibit roughness or brunelling of the needle bearing contact surfaces, and there was no play. Taking the lifters apart is relatively easy. I'll show exhaust number 8 now, and maybe discuss lifters at another point in time. The external body has some scuffing wear, but not that unusual from what I've seen with small block Fords at this mileage. As I've said before, this lifter's wheel and needle bearing showed no failure. No roughness, no excessive play, just a good bearing. And in comparison to another lifter, in relatively the same condition. When looking at the internal piston, you can see some scuffing or wear. These surfaces have a very tight tolerance, and can lose hydraulic integrity with only a little wear. The second lifter disassembled for comparison shows some of the same. It's impossible in a home shop to determine anything wrong here. From where I could view, the cam lobes looked fine. So a quirky lifter at the back of the block that required the rear cover to be removed. No need to go deep into the block, or so I thought. For this video I'm moving on to removing the oil cooler. There will be a separate video on the heads and another on the block decks. This is just an inspection. After 4 years of service I had to replace injector 5, and my biggest issues was a long stem valve cover bolt at the heater box that I had to cut. I couldn't understand why it was there. Apparently the bottom of the cooler is marked with the motor's build date, along with some other production notations. Maybe the 20th motor ever assembled by Pat. After removing the oil cooler, it's time to drain the swamp. And here's the surprise. A perfectly preserved valve cover bolt. One of the shorter types for the lower passenger side, by the heater box. Over time, I had an incremental increase in the differential between the oil and coolant temperatures. This was despite having the dealership install the ELC coolant I had been using in the truck. This cooler's passageways were totally free of any gel buildup, so that was not the issue. However, with the in-feed port section, you can see particles clogging each of the plate's feed. You have to ignore some of the aluminum chips from the sectioning method. This is not rust or sand. It's like a phenolic coating that breaks apart rather easily, but not from water flow. What I don't know is if the rebuilder put something in the cooling system to prevent it from rusting while the engine is in storage. This didn't come from the other cooling system parts. Before this motor was installed, the cooling system was flushed extremely well. The coolant passages in the block do show some rust. Using a bore scope, I investigated the cooling jacket of the block. There was some rust with this freshly opened motor, but nothing like deposited on the cooler intake port. And there wasn't any suspicious coating that I speculated about. What I did find I call a casting bridge between the cylinders, which also had casting sand particles attached. This would be the particles that some people see in their coolant filters. Remember, this block had an original life, was then recycled, then run for an additional 75,000 miles. If someone tells you there can't be sand in the cooling system, remember this image. After removing the valve cover bolt and the pump reservoir, I looked at the fine mesh stainless steel screen in the intake port. While it was free of rips, it had caught some light debris. The particles were non-magnetic, so I expected to find some scoring within the oil pump cavity. The debris were not what I cared to see, although there's not much of it. And I never experienced a complete loss of oil pressure. For a few hours I had moved my fuel pressure sensor to the oil cap. My interpretation was I had a slight decrease in oil pressure than those that had an oil pressure gauge set up in their truck. The oil pump cover showed slight marring of the rubbing surface, but not exaggerated. The main cover surfaces were relatively free as well. The oil pump gears were free of impressions of hard material being run through them, all good to reuse. But the front cover needed to be removed in my attempt to address the deck surfaces. Those that know me understand the debris on the screen will weigh heavily in my thoughts over time. Where else would non-magnetic debris come from? Possibly from the thrust bearing if the crank journal was not machined well. While the engine has its own indicators, the crankshaft and camshaft gears were marked for synchronization. I pulled a bed plate that holds the bearings that are the most loaded. Starting from the front bearing, we can see a single scratch from debris. There is some wear, but it's had a 75,000-mile journey. Number 2 bearing shows traces of the crank's machining marks, and a bright spot from a speck of dirt under the bearing shell, and some side wear. Side wear is not abnormal, it's how the crank moves under load. When looking at number 3, we can see deep gouging in the bearing shell from debris. We can see where it gouged deep enough to expose the third layer of base material. This would account for the quantity of metal on the high-pressure oil pump screen. Some might expect this bearing material would be caught in the oil filter, but most oil filters are bypassed at cold startup when viscosities are high. There is a 20 psi differential bypass valve in the oil filter body. Number 4 bearing I would say is relatively normal. The rear number 5 bearing also looks relatively normal with a minor scratch, side-loaded by the cam gear and torque converter. With the number of scratches and gouges, I would say cleanliness wasn't the highest priority on this engine build. And the list a predictor of things to come. I'll jump ahead with the crankshaft out to complete the bearing review, but we'll return to before the crankshaft was lifted. The unloaded upper bearings were mostly unspectacular in contrast to the bottom-loaded bearings. Number 2 in the center indicates some debris under the shell, causing a small area to be proud and worn. Number 3 bearing, the partner of the scored lower bearing, has some minor debris scratches. Again, the debris was most likely ejected to the side during rotation, or may be broken apart depending on what it was. I carefully inspected the oil pan, and there was nothing retained. The number 4 thrust bearing has some interesting traits that I don't know how to comment on. It's not surprising that it's mostly the bottom shell that has issues. With the shaft loading, there would be clearance at the upper regions for debris to eject out with the oil. Number 5 bearing shell, nothing really interesting here. The concern at this point was if the debris was in the oiling system, did it hurt other bearings or journals? If it came from upstream, the camshaft was at risk, or something could have been distributed from the crankshaft journal to the connecting rod journals, and screw those up. The crankshaft journals were in good shape overall. But number 3 journal displayed some marks from the debris that gouged its bearing shell. But it's a crankshaft that can continue in service. Time to go back a few steps before the crankshaft was lifted off the block to expose the upper bearings. After pulling the connecting rod caps, quick visual of the bearing shell fitment in the connecting rods. Rods 7 and 8. Rods 5 and 6. Rods 3 and 4. Here we have a misplaced locating tab. The shell is off to one side, almost contacting the other connecting rod. The locating tab is there, it's just crushed. I'll move to rods 1 and 2 to show how it should have been. The shell's tab was off to one side, and once the connecting rod was fastened down, the locating tab was compacted. Now I'm lifting the crankshaft out of the block with the engine crane. The shell springs a little bit, and the tab issue is a little bit more prevalent. Bearing wear on the opposite side is severe. The shell was twisted and distorted. As it is, it's impressive that the bearing didn't spin. When you look at the side of the shell, you can see where some material was knocked out. probably from hitting it against the block during assembly or another object, which slightly dislodged it as well. The connecting rod showed no unusual effects from this. And the piston pin showed no higher amount of movement than the other pistons. Pulling the piston further down in the bore later on without dislodging the rings showed no abnormal skirt wear. This connecting rod's cap bearing, the loaded side, only shows the distortion commonly seen if a shell is oversized in length, a result of the top shell twist. A visual inspection before the cap was installed should have caught this. Again, aftermarket bearings, not OE per the video. With the crankshaft removed, it was easier to do a visual check of the camshaft, and on initial glance, it looked okay for 75,000 miles. Wear doesn't change because of power output. I'll do a video later of checking the bearing clearances. They were the OE bearings, free of scoring, but measured at the broader specifications of diameter. That's unusual for 75,000 miles. Unless they were never changed. Maybe that's why they're not the Cleveite aftermarket as all the others were. I'll build up to this one. What this pretty much looks like is a nice camshaft, free of any major issues, not really bad for 75,000 miles. But it always had very good synthetic oil in it. Measuring the journals should be done, and it's a detail I wanted to know based on the bearings condition. How much clearance did the camshaft bearings have? And all of these came right in spec. Very good. On the first lobe to the front, you can see smearing of material. Possibly the main bearing debris got moved through the oiling system before getting caught in a high-pressure oil pump screen or the oil filter, but overall looked good. With another set of lobes, rotating the cam, we can see the wear trace changing. Narrow when the valve is closed, becoming wider under the higher spring load when the valves are open. And during the opening and closing ramps, there's some scuffing on the surface. The lifter's roller wheel sliding on the lobe would cause this. Not abnormal for this ramp. You can also see little specks of metal pickup or transfer. Again, not uncommon. For 75,000 miles, these lobes look normal. Then we get to lobe 8 exhaust. The leading ramp has a few issues, including a good gouge right at the edge of the roller track. It exhibits the normal scuffing from the roller sliding and some pitting. Pitting I may discuss in another video. Then we have the trailing side, a bigger gouge, and pitting. And something has skipped across the surface in front of the roller, leaving chatter marks. These chatter marks could have been minor debris that also caused the gouging in the main bearing shell, or just the debris from the main bearing shell. If we look at the interior of the block around this area, there are no scars from something that had the potential to do this to the lobe. The lifter from this location is intact, free of any indicating abnormal contact with the camshaft. In the remanufacturing industry, camshafts are ground and reused. You just remove enough material around the entire surface while keeping the amount of lift, the distance between the base circle and the lobe peak. But there's a limit on how far you can go without re-welding the lobe, or you leave the grooves of a failed lifter, which is what I think happened here. And this cam may have been someone's judgment call, the way the wheel tracks. Here's one I just didn't conceive of, and didn't catch the issue until putting the motor back together. This motor's just full of surprises. I knew I had variation with piston protrusion. That could be a tolerant stack of parts, or bent connecting rods, but I didn't see that trait in the wear of the connecting rod bearings. The service manual states a protrusion with no variance. Online, there is some discussion that the rebuilder's information states a tolerance of 0.0254 to 0.0354, so I didn't pay too much attention. But with the installation of an aftermarket cam that required 30,000ths of an inch piston to valve clearance, this took a new significance. This protrusion varies front to back, and other than ideal consistency of cylinders 1 and 2, the other cylinders show variation off the same journal, and not a consistent variation down the block as a mislocated crank main bore would show. A bent rod will affect protrusion, but not piston stroke, and the rod bearings looked okay. So back to measurements. Using extensions on a dial indicator, I can find the bottom dead center, the lowest movement of the piston. And using a setup with a vernier caliper, I can measure total stroke of all the pistons. Cylinder 6 is the best video example. You need to make sure you're taking a straight measurement. And it measures 4.126 inches, 0.08 of an inch under the stated stroke, with brand new bearings and no excessive play. So entering the measurements into the spreadsheet, we can see the same trend of stroke and protrusion. As we get to the rear of the motor, the stroke of each cylinder pair decreases, and we still see variation between the same crank journal pairs. The front pair of cylinders displays a consistency of about 0.04 of an inch under stroke. Here's a dirty little secret of some in-house engine builders. If you think you need to deck the block with a high compression motor, you need to shave off the pistons to maintain the same clearance. That, however, is visible on a short block situation, or a problem if the pistons have an identifying mark for installation. Rod journals are offset to the main crankshaft journals, and the difference at 180-degree rotation gets you the stroke of the motor. If you machine the journals to renew the surfaces, it's a straight reduction of 10, 20, 30,000ths of an inch. But there's a process used in the hot rod community. It's known as destroking, reducing the stroke. And with in-house engine rebuilding, you can destroke the crank so you can get more deck material to remove without touching the pistons. In a low revving motor, you don't notice any issues of balance. If you are regrinding cranks to sell by themselves, you target the stated value. Keeping the stroke or destroking, you still need to maintain the indexing on the journal. Or if you're sloppy, you induce an offset. And that lack of proper index will show up in a variation with the cylinders on the same journal. One side has a higher protrusion than the other, and depending on location, you can also have a different stroke. But usually the deviation is smaller. Now you could have a protrusion issue if the block is not machined off the crankshaft journals, but the stroke values on this tell a different story. A crankshaft grinder is just a lathe, with two chucks that sit on an indexing base. And for every rod journal you have to reset the head and tail chucks properly. Some call it an art form. From my point of view, about 6 months as a journeyman earns you the skill set. It's not hard if you understand the concept, but as all things machined, it's about the setup. While reworking the heads and gaskets on this motor, David was kind enough to measure his block's piston protrusion, and it has the consistency between the cylinders you would expect. The need to buy a $700 cam gave me pause about continuing. I never conceived someone would be so careless the crank would be off at registration. It ran for 75,000 miles. At the time of engine removal, the thought was I'd have to replace this one simple part, one head gasket and a main seal. Relatively inexpensive parts for the labor in front of me, and the only issue expected with this motor. The truck had been parked for several weeks, so the oil drained down, and a leaky lifter can require some time for the lifter to pump back up, as it did. In the video of Dynamic Diesel's Stage 1 camshaft comes a warning that the 6.0's original length push rods have to be reused due to the decrease in the base circle. And I think that's another possibility that caused the exhaust valve to not fully open at the time of the long-awaited start. This motor had the shorter 6.4-liter push rods installed. I would have expected this Ford-supplied rebuilt motor to have a new camshaft, but then there were a lot of my presumptions about this motor that were different than reality. Let me review in order the items that were outside of my expectation, and I would put all of these in the category of quality control. Block deck surface machining was outside industry targets, both with the surface finish and the consistency side to side. Unless you want to say they're both crap, and that's an engineering technical term. While I appreciate spare parts, misplaced parts seem to show a lack of attention. Debris left within the envelope of the block causing bearing grooves. Mishandling of assemblies or assembly inspection causing a bearing issue that could have easily led to failure. The camshaft. I really don't know what to say about the camshaft. If you had one of these issues in 1,000 rebuilt motors, I would say you have a quality control problem. Having all of these within one motor is beyond belief. I think the term is travesty. So I'm trying to figure out how one motor, and an expensive one at that, can have all of these concerns. This goes beyond disappointment and regret.